This video is going to go over the concept of inflection points. This is from section 4.2. But in this particular video, we're going to be given the graphs of a derivative of a function and the second derivative of a function. Okay? And the point is, how can we tell where the original function is going to have an inflection point if we're given, for example, only its derivative, or if we're given just its second derivative? So you can see in the two pictures here I have drawn, on the left is the derivative of a function f. On the right, it's the derivative of a function, the second derivative of a function g. So the goal is to find the inflection points of f, for example, in this left picture. And on the right picture, it'll be find the inflection points of g. And you see the pictures look the same, and we'll see how should we be thinking about things when you have the first derivative or as opposed to the second derivative, and vice versa. So let's look at this picture first on the left, f prime, and I want to find the inflection points. So remember, what does it mean to be an inflection point? It means that the concavity changes. Well, how do you know that the concavity is going to change? You know that something will be concave up when the derivative is increasing. So all I have to do is find where the derivative is increasing. That's going to tell me where it's concave up. On the other hand, to tell if I'm concave down, I can check if the first derivative is decreasing. And so for an inflection to happen, the first derivative, needs to go from increasing to decreasing. So let's find those points. Or vice versa, decreasing to increasing. So we notice here to the left of this green line, the function is increasing, and then after it, it decreases. And it decreases all the way up until this next green line. Okay, and then it increases after that. So where's the concavity changing? Well, let's see. Let's just draw these green lines all the way down. Okay, let's call this point A. Let's call this point B. Here's the x-axis. I'm just sort of projecting it down here, just redrawing it. The first derivative is increasing here, and then it decreases, and then it increases again. So concavity is changing here because the first derivative is increasing. The concavity changes across the point A because it goes from increasing, the derivative goes from increasing to decreasing. On the other hand, the concavity again changes from across the point B because the first derivative is decreasing and then increasing after that. And so you see we have concave up. So I'll just call that Cu, and it changes to concave down when we're here, and then it changes to concave up again. And so the conclusion is, therefore, the inflection points are x equals a. Let's put it in another color. X equals a and b. Okay? Because it's where the derivative changes from increase to decrease or decrease to increase. Now let's switch gears. Let's go to the second derivative, right? So this picture on the right. And remember, we want to find inflection, so we want to find where the concavity of the original function g is changing. The concavity of the original function g. Well, we already have the second derivative, and we know that the concavity, that when the second derivative is positive or negative, we get concave up or concave down. So really all we have to do is find where the graph of the derivative changes from positive to negative, or negative to positive. And, well, let's see. Let's get the green pen out again. Here, the function is negative. And then up here, the second derivative is positive, it becomes negative here, and then positive again. And so right here at this point, where it's 0 here, where it's 0 here, and where it's 0 here. Alright, so let's just, again, project that down. Here's the x-axis. Let's call these points A, B, and C. The second derivative is negative, then positive, then negative, then positive. Alright? And so notice here, because the second derivative is negative, the function must be concave down here. Then it must be concave, the original function, g I'm talking about now, then it's concave up, then it's concave down, and then it's concave up. And so there are inflection points where, therefore, we have inflections at x equals A, B, and C. So you see, the way you think about these is very different. Even though the pictures were the same, the fact that they represented different functions told us that the inflection points of the original function actually are different. See, in the left picture where we have the derivative, we only had 2 inflection points, whereas on the right we had 3 inflection points. If the function had a second derivative that looked like this purple graph, then we'd have 3 inflection points. Okay, there's one more point that I'd like to make here, and it's the following. Notice that all these points on the purple graph, the graph of the second derivative, all those inflections happened when it became 0, when it crossed the x-axis. Is that going to happen all the time? And the answer actually is no, because let's look at this. I'm going to erase a little bit. I'm going to redraw the graph just like this. What happens if it goes to 0 and it just boop, just touches it a little bit and then goes back up, doesn't become negative? So what's happening there? So let's draw this, extend the x-axis a bit. So what's happening right here? Okay. So let's circle that point. What's happening right there? Well, you'll notice that there, the second derivative is indeed 0. Let's call that point D. But the second derivative does not change signs. So you see, it remains concave up even after that point D. So that means that the original function g didn't change concavity. And so by definition, you don't have an inflection point. Alright? So let's just make that clear. This D is not an inflection point because the concavity doesn't change across it. Alright, so that's just to make the point that just because your second derivative is 0, it doesn't necessarily mean that you have an inflection point.